looking at space figures. Some reminders from the plane figure geometry that we did before. We have those basic ideas. Point, line, and plane, and kind of everything else in geometry pretty much comes from this right here. We added on to those basic ideas the idea of angle between rays. But there's other kinds of angles that we measure out there, like just kind of a cross section here. Imagine where a wall meets a floor. When two planes meet, oops. So again, imagine this is just kind of looking at the side of a wall, just edge view versus a floor. Those are some examples of where planes come into our reality. Where planes meet, it's called a dihedral angle. There we go. And the di just means two, and hedral is I think it's Greek for plane. So two planes meet, they get a dihedral angle. And there's some good pictures of this in the book, but I'm not so good at drawing them. I guess I can try. If I draw a cube, we can get an idea of dihedral angle. So here's my 3D perspective on a cube. So instead of a floor, I've got this ceiling up here. And then that ceiling meets this wall over here. And there's this angle that they make, which I can kind of see on this face right here. And so that angle where two planes meet is called a dihedral angle. And it's like the angle that these two lines meet at. And so, for example, this dihedral angle is the same as the angle on the edges of this face right here. There's a 90-degree dihedral angle in this cube. So just a note, cubes have 90-degree dihedral angles. Some other things that are interesting about the cube is this ceiling here and this wall right here are called perpendicular, and perpendicular has to be with a 90-degree angle. We talked about that back in section 1 about angles. So some faces of a cube are perpendicular. On the other hand, if we imagine like seeing through this cube here, so let's put some dotted lines like we're looking through it, then I get this floor down here. And so some faces like this ceiling and that floor are parallel instead of perpendicular. So perpendicular again is a 90-degree angle. In this case, it's a dihedral angle because we're referring to two faces instead of two lines. But some faces are parallel in a cube, and those would be opposite faces. It's got too many P's, doesn't it? So just like with lines, some of the things we know about angles, perpendicular and parallel, they come up again when we talk about 3D shapes instead of 2D shapes. So again, the space figures here, we're doing 3-dimensional shapes. Now, there's, again, tons of different kinds of three-dimensional shapes out there. We're first going to focus on a kind of shape called polyhedra. There we go. So polyhedra are 3D shapes with flat faces. That would be planar. So example of something that is a polyhedra and something that isn't, well, the cube is a great example of a polyhedra. It's got these flat planar faces. Right? So by flat, I mean that face right here lives in a plane. So there's my cube. On the other hand, cube is polyhedra, or polyhedron singular. If I were to draw a cylinder, the surface out here on the cylinder is not flat. It doesn't live in a plane. So this is not polyhedron. Although it is closely related, it isn't technically a polyhedron, again, because it doesn't have a, although this circle at the top is in a plane, the circle at the bottom is in a plane, this side part of the cylinder is not in a plane. So some shapes are polyhedra, some shapes are not. Some shapes are easy to be classified because we have nice names for them because we use them often, and others just don't. So when we look at a polyhedra, just a couple of things about the terminology. This shaded part right here is called a face. In slang, we often call something like this a side of the cube. But the problem with calling that a side is when we just focus on a 2D shape like a square. The problem in 2D is we often refer to this edge right here as a side also. So we can't call this a side and call this a side because that's confusing. So side is not really a technical term in geometry. This piece right here would be called an edge. And I talked about that before. I just wanted to remind you. So, so this square has a single face right here, and it has 1, 2, 3, 4 edges. This cube has several faces. It also has a bunch of edges. So there's an edge, and here's an edge. So let's use a new color. Green's fine. So that would be an edge. That would be an edge. So this has a whole bunch of edges. So faces meet at edges, and edges meet at vertices. So that point where these two edges meet would be called a vertex, or plural would be vertice. So this one right here, we could say vertex. And if I refer to multiple of them, it's vertices. There's plural. Multiple edges are just edges, faces are faces, but vertex versus vertices is one of those weird plural versions. When we classify polyhedron, we often do it by the number of sides that it has. So a cube here, sorry, I used slang, the number of faces that it has. So this particular cube, as far as faces go, it's got this one I kind of scribbled on in blue. It's got another one, let's see how about we shade that in red. So there's another face there, 2. We have another face here, 3. And then each of these has an opposite parallel face here. So the cube, there's an opposite parallel green face. There's an opposite parallel floor here for the red, and there's an opposite parallel to this face right here. So a cube is a 6-faced polyhedron. Some other things we can note about the cube here is that adjacent faces are perpendicular. So just like we have different ways to classify flat shapes like squares and quadrilaterals and parallelograms, we have these ways of classifying polyhedra. The primary way is just by the number of faces. So another name for this cube could be like we used hex for 6 before, it could be called a hexahedron. So also known as, AKA, a hexahedron. But it turns out there are other shapes that have 6 faces that aren't cubes. So I'm just going to switch cameras for a second to show one, and then I'll do my best to draw it. Wish me luck. Let's see, stop. Okay. Here we go. So this one, I have this little kit of magnets and rods, and I'm kind of pointed up one of the pointy vertices here. So here I have 1, 2, 3 edges meeting at this vertex right here, and 1, 2, 3 faces. And I can flip it over. This one was pointing down, now it's pointing up. It's identical to the way it went this way. Now if I go, I'm going to call this the sideways view of it. This vertex right here, I don't know if it's hard to see on the camera. This one right here has 1, 2, 3, 4 edges coming into it. So here I have 1, 2, 3 edges coming in. Here I have 4 edges coming in. So that's pretty different to the cube. On a cube, if we pick any vertex like this one on the top, there's always 3 edges coming into it. No matter which vertex I pick, the cube always has 3 edges coming into it. 6 faces, but the edges occur differently. 6 faces, right? The edges occur differently. So this is a hexahedron also, but it's a different kind of hexahedron than the cube. So just like there's a lot of variety in 2D shapes, there's a lot of variety in 3D shapes for any given number of sides. Can I draw that hexahedron? So it started off like a pyramid with 3 edges. So we can see those there, and then it came down like this. That's my best attempt at it at the moment, trying to draw it. So again, the downside of being online is it's hard to deal with shapes like that without some camera or some program that allows you to make these things and spin around. And there are some of those out there. We're not going to get to those today. All right, so other types of shapes. I mentioned the staircase a minute ago. So let's see if I can draw that. So my staircase shape, let's see if we can classify it. So it looked something like this right here, but it was 3-dimensional, headed out kind of like that. So like a staircase heading into a house. That's what I'm trying to draw there. So the faces on this staircase, these are, I meant those to be flat faces. So this has some different kinds of flat faces. Here's one of the flat faces there. And that one I had built a moment ago, it's not quite the same as this one, but close. Had a parallel one on the other side. So this is a polyhedra. Because it's made up of these flat faces here, and it has faces, edges, and vertices. Remember, vertices are the points we meet at, edges are at the edge of the faces. And this is polyhedra because, again, it's made up of these flat faces here. Now this one is a little bit different because it kind of caves in on itself. And the cube didn't do that, nor did this hexahedron over here. So we can kind of classify again that way, and we talked about this a little back in the last section. This polyhedron is concave. And these other ones I had, like the cube, was convex. And a couple ways to get the idea of convex versus concave is this thing kind of caves in on itself here. So that's one way to think about it. And the other way to think about it is if you try to connect two vertices that aren't already connected, like this one right here and that one right there, and the connection between them is not inside the shape, then it's concave. So if it's concave, this is kind of one of the technical ways to think about concave. There are diagonals that are external to the figure. Whereas the cube, any two vertices that aren't already connected pass through the cube itself. So if I try to connect this vertex to this one down here, that has to go pass through the inside to make that diagonal connection. If I wanted to connect, say, this one right here to that one right there, I'd have to pass through this face here to connect them. Right? So all these diagonals are part of the actual shape, whereas here, that diagonal, and a diagonal is any line segment you make that connects two vertices that aren't already connected. That's a diagonal. If there's any diagonals that are external, then that's one way to classify something as concave. So polyhedra have flat faces. They also have edges and vertices. They can be convex. They can be concave. With 2D geometry, we studied regular polygons. So I just want to remind you about what a regular polygon is. It's kind of a new topic, regular polygon. Means it's equiangular. All the same angles. And equilateral. Meaning all the edges are the same length. So equal angles and equal edges. So some examples of regular polygons were a square is a regular quadrilateral. And then we have what the equilateral triangle would be another one. And then after that, we just call them regular this or regular that, like a regular pentagon or a regular hexagon. And so I would just have to draw a hexagon, and we practiced drawing this with GeoGebra last week. When we draw, we just want to make sure all the angles end up being exactly the same measure and all the sides are the same length. So I'm not doing a very good job of that here, but all of these have to be the same length. So we usually mark them like that to say we meant them to be the same. And all these angles should be exactly the same measure. So I work my way around. And there can be a regular 3-sided figure, a regular 4-sided figure, a regular 5-sided figure, 6-sided figure, 7-sided figure. You could have a regular 100-sided polygon. Right, so these just keep going. Regular 100-gon, and so on. When we start to look at 3-dimensional regular shapes, it gets a little more complicated. So regular polyhedra. All of the faces must be congruent, same size, same shape. So it has to have congruent faces. All the edges have to have the same measurement, so they have to be congruent edges. Now, angles, there's a lot of angles going inside a polyhedra. We go back to when I was talking about the cube over here. There's the idea that this edge here and that edge here meet at an angle. but these two faces meet at angles also. So we have these dihedral angles between planes, but we also have angles between edges. And the other thing to consider is where the vertices are, the number of edges that head into that vertex. So like on a cube, there's always 3 edges heading into every vertex. But when I made this hexahedron here, this vertex at the top was where 3 edges came together, but this one on the side, oops, I'm going to switch color there, blue or yellow maybe. This one on the side there, I can't hardly see the yellow and blue. This one had 4 edges coming into it. So there were 4 edges here. But there were only 3 edges here. Right? So that's irregular, right? They don't match. Regular, everything's got to match. So congruent faces, congruent edges, we have to have the same number of edges at each vertex. And all of the dihedral angles have to be congruent. And again, regular versus irregular. There's more things that have to be regular on a polyhedra because we have more dimensions. And it turns out that makes things a bit more restrictive than in 2 dimensions. So there's infinitely many regular polygons in 2 dimensions, but it turns out in 3 dimensions, there are only 5 of these regular polyhedra. I'm going to try to show off my versions on the camera first, and then I'm going to go online to some pictures of them. And again, there's some evidence that with kids, the more shapes they play with, the better their math abilities are later, their ability to, think 3-dimensionally comes from practice. So having these kinds of toys in the classroom is a great idea. So let's play with some toys. All right. So, where'd you go? Just modify this sucker. This right here has 1, 2, 3 faces and one on the bottom for a 4th face. And every vertex has 3 edges coming into it when I look at it. And each of these faces meets at the same angle. Faces are all these same size equilateral triangles, and I have exactly the same length edge on each side. So this is a regular 4-sided polyhedron. We came across it a couple weeks ago. It's called a tetrahedron. Tetra is a abbreviation or a different word for 4. So tetra, 4 hedron faces. This has 4 faces. Tetrahedron. And it's the, I guess in a sense, kind of like the smallest regular polyhedra because it only has 4 faces. You can't get any fewer than 4 faces for a 3D object. All right, so then we have the cube. So got my little dice here. It has 6 faces. And every face is a congruent square. Every edge has the same length. Hey, Evely, we are playing with toys. Let's see if it has audio now. This is a cube dice. And is my view correct? Let's try that. What else do I need to say about it? All of the angles are right angles. The dihedral angles are 90 degrees. So this is a regular 6-sided polyhedra. We could call it a hexahedron. It usually is just referred to as the cube. All right, then this dice is different than that hexahedron I showed before because it has 4 triangular faces on this side. And if I flip it over, it's got 4 that way. But it turns out I can pick any vertex to be like the top pointing vertex. And the thing has exactly the same shape when I look at it. So it doesn't matter which vertex I call the top and the bottom. You can't distinguish. I mean, this has numbers on it, which makes it distinguishable, but you can't distinguish between one vertex and the other because all the edges meet at the same angle, all the faces meet at the same angle. There's the same number of vertices coming out of every single, or same number of edges coming out of every single vertex. This has 8 faces, so it's called an octahedron. And it is regular. So far we have a 4-sided tetrahedron. We have a 6-sided regular polyhedron, that's the cube. We have an 8-sided regular polyhedron called the octahedron. Now I have this dice here that's got 10 sides, but it turns out if you look at it at a different angle, then weird things start happening with the vertex and the edges. So I have some, these edges are irregular compared to these edges, they don't match. So this is a polyhedron. It's got these kite type faces on each side, but it is not regular. Turns out there is not a 10-faced regular polyhedron. The next one that ends up being regular is this 12-faced polyhedra. It's got the numbers 1 through 12 written on them. And every face is a congruent pentagon. Every vertex has 3 edges leading into it. And all of dihedral angles, the angles connecting the faces, are congruent. So it turns out the next shape in line after the tetrahedron, the cube, and the octahedron is this 12-sided, and it's called the dodecahedron. So dodec, 2 and 10. I'll write these down in a sec with some pictures that are better than I can draw. After 12, it turns out you can't find one that has 13 faces or 14 faces or 15 faces or 16 faces or 17 faces or 18 faces or 19 faces. 20 is the next one. And this one is made up of equilateral triangles. Every vertex has 5 edges that go with it. All the dihedral angles are the same. So this is the next and last regular polygon. So there's only 5 regular polygons. So in 3 dimensions, there's only 5 regular flat-faced objects, whereas in 2 dimensions, there's infinitely many. You pick a number of faces, there's one, but not in 3 dimensions. Whoa, it's kind of crazy.